This question, we're asked to diagonalize a 3x3 matrix. We are going to do basically all the same steps. So step one, we're going to get our eigenvalues. So as always, lambda I minus A, that 3x3 matrix. And I'll get the determinant of this. So I am going to use just that second row to find the determinant. That's going to make my life a lot easier. So if I do that one, it will start at, just to make sure I'm kind of following the right patterns, but it'll be positive in the top left. It'll be like -0 plus lambda minus 1 times the 2x2. And then minus 0. So I get lambda minus 1 times lambda minus 2 squared minus 1, which is lambda minus 1 times lambda squared minus 4 lambda plus 3, which is lambda minus 1 and lambda minus 1 times lambda minus 3. And so what we can see is that we do have 1 showing up twice. So I'll have lambda 1 equals 1 and lambda 2 equals 3. So we only have 2 eigenvalues. That doesn't necessarily mean that this thing is not diagonalizable. Diagonalizability depends on the number of eigenvectors we get. And so what we want to look for here is that we do have this lambda 1 equals 1 that has multiplicity 2. It may actually generate 2 eigenvectors. So that's how we're going to determine whether or not this thing is diagonalizable. It is okay to have less values. So I might as well start with lambda 1 equals 1. If I only get 1 out of this, then I know that this thing won't be diagonalizable. So because this is the one with higher multiplicity, it's got to have that many vectors. So we're just going to see what happens. So I'll plug that in for lambda. I get -1, -1, -1, 0, -1, 0, and -1, 1, and -1. And so when I check this out, I can see I've got, yeah, I'll just do my row reductions here. So we're trying to find the null space. So I'm going to add, subtract the first row from the third. And that should give me a 2 and 0. And I'm kind of seeing here that it looks like I'm going to get 2 pivots for this. And I can cancel out that 2. What I'm going to have is the free variable here. And basically what this equation is going to say, let's call this z equals t. I can see from the second equation that y equals 0 must be true. And then this first equation is going to be basically that negative x minus 0 minus t is 0. So x is negative t. So the eigenvector that I have for this, I'm only going to get the 1, is going to be, if I set t equal to 1, I'll get this vector here, -1, 0, and 1. And so it's only 1. That is mostly enough to conclude it's not going to work because the multiplicity is 2. And so if I was to get the extra eigenvector, it's going to come out of this. But I'm just going to kind of show you that for the other one, we're only going to get a single eigenvector. So I'll do my 3i minus a, and so I'll get 1, -1, and -1, 0, 2, and 0, and -1, 1, and 1. And so pretty much here I'm to see, yeah, that bottom row is just a multiple of the first one, so it's going to get wiped out. Same thing I've got that third one's going to be free. It's just going to give me a slightly different equation here. So z is t, this is y equals 0, and this one's going to give me x is t. So my second eigenvector is actually going to be 1, 0, 1. And we've only got the 2. It's not enough. And so it's not diagonalizable. So the really, really important thing to note here is that I'm not able to make that conclusion just from the number of eigenvalues. We absolutely have to go and get the vectors that go with it and make sure that there's only, make sure that we have like a certain number of eigenvectors. We have to conclude that it's not diagonalizable, make sure that none of those eigenvalues are actually generating more than one eigenvector so that we still get that count. In this case, like we didn't get that. We only got one vector from each, a total of 2. We need 3 in R3. So it's not diagonalizable.